Okay, welcome everyone. Today we're going to have a talk by Alberto Cattaneo, and he's going to tell us about a cohomological view of quantum field theory. So please take it away.
Okay, thanks for inviting me. And so this would be some general overview of quantum field theory, especially in the field, in the BV and BFV formalism, some related stuff, also including some recent developments. I will be very general with little details, but of course, feel free to ask for more. So first, let me remind you, well, very shortly, everybody knows that, but just let me remind you what is field theory, especially from the point of view of action function, both the classical and the quantum version. The idea is that you have a space of fields and some function, the action, on it. And of course, typically you have extra requirements, for example, locality, which means that, well, the space of fields, I mean, first of all, the fields are supposed to be something local. So sections of some sheaf, for example, functions, vector fields, connections, maps to some other fixed diagram manifolds, more general tensor fields like metric field. And the action S is then supposed to be an integral over some space-time manifold M of some Lagrangian density, which at each point depends on the fields and on their derivatives, finitely many derivatives. So just to be concrete, let me just recall some very basic examples. For example, the scalar field. In this case, field phi is just a function on M. The action is just written here. I mean, here I use the notation of differential forms and Hodge dual. So there is a choice of metric, or Riemannian or Lorentzian metric on M, and this is just the usual action for the scalar field. Mills field, the field is a connection, I mean, in the connection one form, then you compute its curvature, and the action is defined again by taking the wedge with the star dual, or if you can take gravity, so in this case, the field is a magic tensor, and the action, well, defined, well, computing the scalar curvature, multiplying it by the canonical density associated with the metric and integrate. Okay. Classical field theory, from this point of view, is just a variational problem. So you have reaction, and you look for the points, and these will be some fields. I will denote the set of such fields as a space of solution. Whereas in quantum field theory, I will formulate it from the point of view of the final integral. So formally, you take the exponential of the action and integrate over all possible. Of course, you have to give a meaning to this expression in question mark. Particular, I'm using in theory that have local gauge symmetry, for example, where you have gauge transformations. In this case, you are interested in the version in the space of solution modulo gauge symmetries. And in the quantum version, well, basically, instead of integrating over all possible fields, you should integrate on the quotient space, fields modulo transformation, morally speaking, but actually not what you do. Right? Usually you look some other, some replay of this, as I will explain later on. Now, if space-time has a boundary, then of course you have to, well, consider what happened at the boundaries, in particular, for example, to impose appropriate boundary conditions. And space-time is not compact, and you also have to prescribe the behavior at infinity. Now, in this talk, I will typically think of space-time as compact, but possibly with boundary. Then, okay, somehow the recurring theme in this talk, what is the correct choice of the space of fields? And the point that typically you start with some choice. So, for example, I would say, like, I know my function phi in the field should be, for example, smooth function on M, and you can think of smooth connections metrics, but I could require some lower or differentiability, and there is a boundary. I have only the boundary condition, also how my approach the boundary, and especially if a manifold is not compact, I should also prescribe some behavior at infinity. And what I want to somehow stress is that there is some freedom in this, some ambiguity, and it's good also to have this ambiguity and to exploit it. So, for example, one ambiguity is which regularity condition you want to impose, and even more, a question about, well, how you want to define the space of fields. So one possibility is to really think of the space of fields as some infinite dimensional manifolds of fields of a certain regularity, certain topology, and so on. And if, well, doing something non-linear, it's even not just a vector space, but really a manifold, an infinite dimensional manifold. But of course, for example, in field theory, sometimes so basically all the operations you are local and algebraic. Instead, consider the so-called bidirectional complex, namely you move the jet space and you think of of the action. I mean, you replace the action functional or integral of the Lagrangian density by working on some objects on the jet space. So somehow, then the integration is no longer there. Somehow, integration is just thought of something that kills total derivatives. And another version, which prefer more because it's closer to that somehow the intuition when you use variational problems, right, to undergrad students, and also useful for some other application, is some sort of functorial way. The idea is to, I mean, let me specialize it in the case of a sigma model where the fields considered as met from some fixed spacetime M and some fixed target manifold N. So you want to describe this infinite, well, if you take somehow the standard approach, this is some infinite dimensional manifold. Like you consider maps from end to end over a certain regularity. But actually another way is to think of these things as a functor from the category of manifolds, or somehow with opposite structure, to the category of sets. This simply means that once you choose a manifold Z that you should think of, which you think of as a parameter space, you map it to maps from Z cross M to N. And this actually, well, if you know category theory, you can check that this is actually a functor. And then you can reformulate everything in terms of natural transformation. So for example, the action functional can be thought as a natural transformation from this functor and the function omega 0, which is just a functor that assigned to a manifold, a test manifold Z, is space of functions. And the derivative, I mean, the functional derivative now in this language becomes some universal, the RAM differential, which is natural transformation from the functor omega 0 to the functor omega 1. The functor omega 0 is what I hear, and the functor omega 1 is one that associates to each manifold its space of one-fourth. So from this point of view, basically, I mean, you no longer have to care much about the structure of this space as a manifold and so on. Everything is encoded in this data. Okay, this just as an aside. I will not stress this now. Whatever I'm going to describe later on can make sense in the various versions, so you can think of field theory in the version you prefer. Like just giving this space or whatever space you are considering the structure of some infinite dimensional manifold. You can think of it in the bivariational complex settings or in this setting. It doesn't matter. Okay. Anyway, we'll be very vague and loose about the details. So this applies to everything. The next observation is, anyway, once you've chosen your setting, the space of fields can be changed anyway, because, for example, in classical field theory, what eventually matters is the space of solutions. And you can think of a space of solution inside some space of fields or inside some different space of fields. And from the point of view of the classical field theory, this is more or less the same. And in quantum field theory, if you make sense of the functional integral, you might think of like getting the results by integrating over some space of fields, also a different one, maybe possibly changing the action or not. The only thing that if the two integrals also possibly adding observable give you the same results, they basically are equivalent from this point of view. So of course, one thing you can do is just a change of variables and you keep track of the change of variables, but you can also make more general replacements, as I will explain later on in some examples. Okay, so now let me come to some of the core of the talk, namely this cohomological approach, and somehow I will eventually describe the BD formalism. So first, let me just start from the case of a theory with no symmetries, or more general mathematical problem of describing a subset of a set where the substrate is described by some equations. So we want to describe this space of solution, Sol, which is a space of solution to some equation, which in this case happen to be critical points of the action. Now, the idea is first to move to the algebraic description. I want to think of the space of functions on the space of solutions in terms of a space of functions on the whole space of fields. So in algebra, you realize this, so assuming that this is a closed subset, you can think of the space of function on the space of solution as the space of function on the whole space of fields modulo the functions that vanish on the subset. So this is the ideal generated by this equation. And again, I will not stress exactly what kind of function you want to consider on the space of solution. Depending on the context, you can choose different models. But somehow, once you're fixed the function you want to consider, you have this algebraic version of the space of functions on the space of solutions, and you forget the space of solution. You just work in terms of functions. A cohomological way of describing this is to consider a complex whose cohomology gives you this. So the idea is you consider now two spaces. One space is a space of functions on your space of fields, which is placed in degree 0, and the other thing I consider are vector fields on the space of fields. And I place these in degree -1, and then you have some linear map between them, and the linear map is the following. To a vector field X, you just associate the vector field applied to the action function. So this expression here. And now one can see that if the action is non-degenerate, and this is the case where you don't have gauge symmetries, then the Q I define here is injective. Namely, the kernel of this linear map is just 0. And if you think of like what is cohomology, cohomology at each degree is defined as the kernel of the map modulo the image. So if you stay at this level, the kernel is trivial, and then, well, the image is something that is defined to be 0 here. So the cohomology in degree -1 is trivial. On the other hand, if you want to consider the cohomology in degree 0, then you should take the kernel of the additional map that I haven't written down because it is by definition the 0 map, so everything is in the kernel, but then you have to mod out by the image of this linear map Q. And by construction, the image of this linear map, because here image means you can place in any possible vector field, so the image is the ideal generated by this differential. And so the cohomology in degree 0 is precisely all functions modulo this vanishing ideal, which is precisely the function on the space of solution. So this way we have recovered the space of solution as the cohomology of this two-term complex. You can actually extend this complex on this side, adding bivector fields, trivector fields, and so on. And you can extend these appropriately in such a way that it squares to 0. So it's really a boundary operator. And actually you extend in such a way that it's also a derivation in the algebraic setting. And again, you arrange things in such a way the cohomology is concentrated in degree 0, and it gives you back these functions on the space of solution. So this is what in algebra is called the Kosul-Tate resolution. Now, multi-vector fields, that is, exterior products of vector fields, can also be thought of as functions on a new manifold. So what you do is take your original space of field, takes this cotangent bundle, that is, you have some add momenta, and I place this notation here -1, which means that the momenta now are assigned some additional degree -1 and are considered as odd variables. So this new degree is what in physics is called the ghost number. And and this Q here, which are extended to multi-vector fields, turn out to be a vector field on this new supermanifold. I will explain this in a moment, actually, in this slide. So the idea is the following. First of all, the nice thing of having a cotangent bundle that you have a symplectic structure. So I use some finite dimensional notation. So I denote by phi I the coordinates on the space of field, and by phi dagger lower I the corresponding momenta, the coordinate on the cotangent bundle. So in this notation, these 5 variables have degree 0 and are even. These phi dagger variables have degree -1 and are odd, but still I can define this symplectic structure, these two forms, this non-degenerate closed two form. And then I define my Q, so exactly the Q that appear here, as the Hamiltonian vector field of the action. So I want this equation to be satisfied. And you see here very easily that this Q is this vector field, namely its component in the phi dagger I direction is the partial derivative of S in the ith direction. So to be more explicit, this is the S with respect to the phi. Okay. So in particular, you see that the image of Q is the ideal generated by all this partial derivative, which is the same as the ideal generated by the differential or the differential of the action. Okay, now things become more interesting if there are symmetries, and this is actually obtained by considering the corresponding, let me do it in a special case where you are some infinitesimal symmetries arising from the action of some Lie algebra. So this means that I have some given Lie algebra G and a Lie algebra map from this Lie algebra to the Lie algebra of vector fields. And now you can encode this algebraically in terms of the Chevalley-Eilenberg complex. So you take the exterior algebra of the dual of the Lie algebra, tensor product, the space of functions on the space of fields. Again, if this really everything is infinite dimensional, you have to say more what this tensor product is, but I don't want to enter into these details anyway. Now, the nice thing here is that you can think of this exterior algebra of the dual as functions on a supermanifold you can define by shifting your Lie algebra by one, in the sense that you think now of coordinates on your Lie algebra to have degree 1, right? And then and think of them to be odd. So linear coordinates, linear functions are element of G dual, and then since these are odd, you're allowed to use polynomials, but in a not variable, and this gives rise to the exterior algebra. So you can encode this. And then you can extend the operator Q I had before to this factor, and you do it this way. So people are familiar with it. This is just what is called the BRST operator. And the idea is the following. So I choose a basis for my Lie algebra. I take the corresponding structural functions, structural constants, A, alpha, beta, gamma, and I denote by C alpha the coordinates on G. And then you just define Q acting on C alpha to be this quadratic expression, which makes sense because the structure constants are odd in the indices beta gamma, but I declare this coordinate to be odd generator here. So this makes sense in this exterior algebra. And then I extend the Q on the functions. So I have a function phi on the space of fields. I define Q of phi as this expression, which is linear in these coordinates on the Lie algebra, so it becomes linear here, and just given by these sums, where here I place the coordinate C alpha, and here I take the corresponding vector field X alpha on the space of fields here. And now the idea is to put everything together. So now what I do is I take the space of fields, cross this Lie algebra shifted by 1, so this is what I had here, and then I take the cotangent bundle of everything shifted by -1. So now over here, I have a symplectic structure. So this symplectic structure I wrote before in terms of the coordinates on F and their momenta. And then I introduce this coordinate C alpha on G shifted by 1 and add their momenta because of this cotangent bundle. So this is the canonical symplectic structure. I extend the action functional by this term. So again, here I use some finite dimensional notation to simplify things. So this, again, is defined using the structural constants. So here I put the coordinates on the Lie algebra, and here I put the C dagger, which is the coordinate on the cotangent fiber shifted by -1 of the Lie algebra. So you have this expression, and now you define, here there is a mistake here, sorry. You define Q. You define Q to be the Hamiltonian function for this extended action. So here I call this BV. This stands for Batalin Vilkovisky, because this is what essentially they consider, well, not exactly the example, you consider an even more general example. I will come to it in a moment, but the idea is that, okay, you extend this action functional this way, call it SBV, and then you call Q the Hamiltonian vector field of this. And well, in this example, this q squares to 0, so it defines a differential, and you can consider its cohomology. And it turns out that in this example, the cohomology gives you precisely the functions on the quotient of the space of solution modulo the symmetries. Of course, here assuming that things work nicely, that the action is nice enough for this to work, for this, in particular, for this quotient to exist. Now, the idea is that you extend this principle also to the cases where the quotient is not nice, and basically, well, you replace the quotient by the complex defined by this differential q. Now, one important remark is that this condition, q squared equal to 0, is implied by the condition that this function s has Poisson bracket equal to 0 with itself. So what is a Poisson bracket? So here we have like this cotangent bundle, this symplectic form. You can associate the canonical Poisson bracket, which I will denote this way here, and you can compute the Poisson bracket of this function s with itself. And the interesting thing is that this is not automatically equal to 0 because this Poisson bracket defined in terms of this odd symplectic structure turns out to be even when you plug in even function like this s here. So this is a non-trivial equation, which implies that this q squared to 0. Okay, so this is called the BV formalism. Actually, this is a BV formalism in the very particular case when you have an action over the algebra. So this sense actually goes back to Batalin, Becker, Histoire, and Tuting. So it's called the BRST formalism. But once I rephrase it this way, in terms of a symplectic form, it's a Hamiltonian vector field, and this equation, this is what Batalin Vilkovisky introduced in the late 70s. And it is more general than just the case when you have an infinitesimal action over the algebra. This Batalin Vilkovisky formalism has become important in mathematics also in recent years. It's been revived in the so-called derived algebraic geometry tag, first by Lurie and then by Pantev, Toine, Baquier, and Bezzosi. And of course, they generalized it a bit, then they consider algebraic varieties, and they actually observe that since, I mean, for their purposes, all these equations can be relaxed in a homotopical version. So for example, this two form is no longer required to be strictly closed, strictly non-degenerate, and so on. We will see something of this, not in the full generality they consider, but some relaxed version is useful also in field theory. Okay, now let me formulate this in the full generality of Batalin Vilkovisky. So the idea is that now we have some graded manifold M. So in the previous example, it was the odd cotangent bundle of the space of fields. We have some symplectic form on this manifold, and this should be, so symplectic means closed and non-degenerate, and of some degree -1 with respect to the degree of this super manifold, and some function of degree 0. And you want this function to satisfy this equation. As Poisson bracket with itself should be 0. This is called the classical master equation. Okay, and we'll just abbreviate it as CME. Okay, and there are some obvious generalization you can consider, namely changing the degrees here. So, I mean, what is interesting is that we want this Q here, this Hamiltonian vector field Q, to have degree 1 by convention, because we won't consider a complex where the coboundary operator has degree 1. But otherwise, you can change the degree of omega and of S, just their difference should be 1. So there is a version which I call BFNV, where this n is the same n as you have here. So the degree of the function S, instead of being 0, is n. And since you want Q to have degree 1, then the degree of symplectic form should be n-1. Now, the BV formalism I was describing here is the case when this degree is equal to 0. So you get F to the 0, so you remove it, and you get BV. So these are small, there are the rules for this terminology. And well, this terminology is chosen in such a way that the other important case, when n is equal to 1, that is this function S is degree 1 and the symplectic form is degree 0, becomes BFV, and well, this is because this is actually a formalism introduced by Batalin, Fradkin, and Vilkovisky to give a cohomological resolution of the reduced phase space. So remember, I introduced this Batalin-Vilkovisky formalism at this level, the classical level, to describe the space of solution of a variational problem modulo the symmetries. There is a version which is also related to field theory, namely when you go to, say, Cauchy surface, and there you want to assign some associated symplectic structure. So this is the reason why in this other formalism, omega has already degree 0. This is actually related to the symplectic structure you want to have on the phase space. And if you have symmetries, you want to reduce this phase space by imposing some constraints and quotienting by some symmetries. And these are all encoded in this BFE formalism. Okay, now let me move to some of what I want to talk about today, namely the kind of equivalences that you can consider in this context, first at the classical level. Now, one very obvious equivalence, since we are talking about like a manifold with symplectic form and some function, one obvious equivalence are just diffeomorphisms that preserve the whole structure. So an equivalence between this M omega S and some M prime omega prime and S prime will be some diffeomorphism from M to M prime with a property that the pullback of the symplectic form omega prime gives you the symplectic form omega, and the pullback of the function S prime here gives you the function S here. Okay, so this is a very obvious equivalence, but it's very, very strict. One remark is that since we define the Q as the Hamiltonian vector field of S, and analogously we can define the Q prime as the Hamiltonian vector field of S prime with respect to the symplectic form omega prime, then these properties tells you that actually, I mean, since it's a diffeomorphism, you also have the push forward operation. You can push forward vector fields, and in particular, it turns out that if you push forward the vector field Q defined here, you get the vector field Q prime defined here. Now, this also means that, of course, you can also pull back vector fields, in this case, just the inverse of the push forward. So in particular, you can define this pullback operation from functions on M prime to function on M, Q. And well, I can think of this now as a map of complexes. So I have a linear map from this space to this space, which transforms this differential Q prime into the differential Q. And since this is a diffeomorphism, this becomes actually an isomorphism. It's an isomorphism on the algebra of functions. And in particular, since it's compatible with the differential, it gives you some induced map in cohomology. So here, remember, cohomology just means that you have to take functions that are killed by Q prime, modulo functions that are in image of Q prime. And since, well, this phi star is compatible with that, you have an induced map in cohomology. Namely, you take some Q prime function here, you can map it to something over here, and it's automatically Q closed. And moreover, if you change the function here by some Q prime exact term, you get something that is Q exact here. So you get a linear map in cohomology, which is automatically an isomorphism. Now, if you think of our original construction, I've introduced these cohomologies to describe the spaces of solutions modulo symmetries. So this is the relevant information. So eventually, what really matters is that you have a way of constructing an isomorphism between these two cohomologies. And of course, this is a good recipe to construct these isomorphisms, but you may use weaker data to construct this isomorphism. So let me give you now a weaker definition of equivalence. Namely, first of all, you just assume that you have some map phi from M to M prime. You don't require this map to be diffeomorphism, just some say smooth map, but you want it to be compatible with this operator Q and Q prime. Namely, you want that for each function on the target M prime, applying Q to the pullback of the function is the same as pulling back what you get by applying Q prime first. So you want this commutativity relation for all functions. And this in particular implies that the pullback is a map of complexes as before, and hence it induces a linear map in cohomology. I will call this linear map as phi star in square bracket. So you get a linear map in this direction. Now, if you have some other map from M prime to M, not necessarily the inverse, some other map which satisfy this condition, this somehow the dual condition, then this map will induce a linear map in cohomology in the opposite direction. I will call this map psi star in square bracket. So now we have a linear map in this direction, a linear map in the other direction, and we're interested in the case when they're inverse to each other. So we say that the pair phi psi is a quasi-isomorphism if the induced map in cohomology are one the inverse of the other. So notice that one possibility is when phi and psi are inverse to each other to start with, but this now is a weaker condition, right? We just have phi and psi as here, and they are compatible with Q and Q prime. And the only condition is that they are inverse to each other in cohomology. And this is actually the only relevant thing. Of course, well, we want them to preserve Q and Q prime, but actually it's better to let them preserve the symplectic structures and the action functionals as well. But now we can do that in some relaxed way. So namely, we can say that the pullback of the symplectic form of omega prime by phi is not exactly the symplectic form we want to have on the space M, but could be that up to some Lie derivative of some two-form alpha by the vector field Q. So this is something that at this point we can allow because eventually we're only interested in working in cohomology. And similarly for the action, we say that we are happy enough when pulling back the action on the target space of fields gives us the action on the space of original space of field up to some Q exact term. And of course, we have to impose the same kind of conditions for psi star. And so one important notion of equivalence of a BV spacey BV manifold is precisely this notion of quasi-isomorphisms with these conditions. Now, why is this important? So let me give you a couple of examples. So one example is when you start with your space of fields M, our example with a cotangent bundle, and we enlarge it by adding some trivial pairs of variables. So namely, for example, in this example, I just add in one new variable lambda, which is the coordinate r and its momentum. So I have to take always the cotangent bundle shifted by -1, and some other variable, let me call it C bar, on r shifted by -1 simply means that this is an odd variable of degree -1, and I have to introduce its momentum this way. And then I extend my original action over here by adding this stupid term, this coordinate lambda times this momentum C bar dagger. Now, if you think what is a Hamiltonian vector fields of this new function S prime, well, it's the old one for the original variables, but there is something that arises here. And in particular, the non-trivial part says that when you want to compute Q applied to lambda dagger, well, this is what you obtain when you differentiate this function by lambda, so you get C bar dagger. And similarly, if you want to compute Q on C bar, you have to differentiate this function by C bar dagger, and so you get lambda, and otherwise you get 0. And so in this complex, you have this cohomology, and this should immediately remind you of something that is similar to the cohomology on essentially on Rn. And so by Poincaré lemma, this cohomology is completely trivial. So you will get this condition that you get this isomorphism of complexes. So these are some trivial things you have added, and you can add many more pairs of this kind, actually even infinitely many. And this is a trick that is used, for example, in quantum field theory to have enough extra variables to write down the gauge fixing in some nice and simple way. A second example that I'm interested in is when you want to actually decompose your space-time into simpler pieces. So the idea is to start with some manifold, some space-time manifold M, and I cut it along some hyper surface sigma into two submanifolds M1 and M2 with boundary sigma. And so I can reconstruct my original manifold by gluing these two pieces together. And I mean, the question is, how can I reconstruct the space of fields on M? Well, the idea that the fields on the whole manifolds, of course, I can just forget the other piece. So of course I should get the fields on the manifold M1, the fields on the manifold M2, but the fields on the whole manifold M are fields on the two manifolds that agree on sigma. Actually, they should agree also with some transversal derivative. So here is some extra information I have to give. But okay, here there are some ambiguities precisely in what extra information I have to give. And so especially if there are symmetries. And so the idea that is nice that we can be flexible here and give different prescriptions to recover the space of fields on the whole manifolds in terms of spaces of fields on these pieces. I will say a bit more about it below. Now let me give you some concrete examples where I really want to change completely the theory, but eventually I get some equivalence theory. So these are two examples of parameterization invariant theory in one dimension. So this is called Jacobi theory. So the theory on the space of paths. I introduce the usual kinetic energy, 1/2 m2 dot square. So for example, take one path in R. And then for some fixed parameter capital E, which actually you should think of the energy, I consider this action function. I'll just take the square root of this E times the kinetic energy. So this is a parameterization invariant action. Basically, it's just the Euclidean length of the path, and you can consider the associated variational problem, which will give you essentially the straight lines. This is called Jacobi theory because it's somehow how Jacobi reformulated the Maupertuis principle. So you start from your original, say, action given by the Lagrangian just the kinetic energy, but then you want to take variation with fixed energy E, and you can rephrase it this way. And then there is a second interesting theory you can construct in one dimension, where in addition to the path Q, you also have somehow one-dimensional metric on the interval AB, and you can consider this Lagrangian. So there is one term, which is the kinetic energy divided by the square root of this metric. Now we're in one dimension, so this is 1/1 metric. So this also its own determinant. And then you have another term here, where you just basically consider the length of the interval using this metric, and you rescale it by this energy parameter. Now, it turns out that classically, these two actions are actually the same in the sense that you can consider the variational problem for the variable g here, look at the critical point, insert, compute the g at the critical point, so this would be a function of g of the path. You can insert it here, and you get back this action. But actually, this becomes a bit deeper if you do express this in the BV formalism. It turns out that you can really construct a quasi-isomorphism in this sense, preserving the structure in this sense here. So from this point of view, these two theories are equivalent in that sense. Okay, now since I want to go a bit deeper into this example, I have to tell you what I should do when my space-time has a boundary. So how to refine the BV formalism in the case of boundary. And now, I start with the problem you have when you have a boundary. So recall that we have some action function of S, some symplectic structure on the space of fields, and we define this operator Q as a Hamiltonian vector field of S. And then everything was encoded in this Q. Now, if this S is actually my action functional, when I compute this differential, right, to formulate it in an appropriate way in order to compute this Q, I typically have to integrate by parts. And if I'm working on a closed space-time, right, there are no boundary terms. So this was how Q was defined. But now, if I want to extend this formula to the case when my space-time has a boundary, I'm in trouble because I mean this formula was okay after integrating by parts, so there will be some additional term here living on the boundary. So let me formulate this going to some more general context. This is what we call the Lax BV formalism. So the idea is the following. We start with the data we had before, F, omega, and S, but now I also consider the vector field Q as some independent ingredient. So this quadruple here consists of some supermanifold F, some close to form omega of degree -1. Typically, it will be non-degenerate, so it will be symplectic, but at this level, I can even remove this condition. And then I have a function of degree 0 as before, and the vector field of degree 1. And I want this vector field to be our differential. So the only condition I still impose is the condition that, well, the Lie bracket of this vector field Q itself is 0. So this is the only condition I retain. But I no longer require this Q to be the Hamiltonian vector field of the function S. So they are now completely independent. So I can compute the error term. So I define this alpha twiddle to be the differential of this contraction and the variation of the action. So this will be a one form on the space of fields of degree 0. And then I can take its differential. So they will give me a two form on the space of field of degree 0. So notice that we started with a two form omega of degree -1 closed. And now we get a new closed, actually exact, two form of degree 0 on the space of fields. So formulated here. And now the interesting thing is that if you look at this equation and how omega twiddle is defined, you can make a very simple exercise and you realize that this new two form omega twiddle is now invariant under Q. Okay, so the idea is that actually probably it's better to move from the original two form, which didn't have good properties, to the new two form, which is now invariant. It's also closed, so it's going to something being symplectic. The only problem that typically is degenerate. And well, the idea that, well, we just remove its kernel. So we take the space of fields, we consider all the vector fields that kill these two forms. They will form some distribution. Actually, since the form is closed, there will be some involutive distribution, and we go to the Lie space. And now I assume some regularity conditions. So one of the regularity conditions that I want this quotient, this Lie space, to be smooth. And let me call it F underline. And then what turns out is that on this quotient space, you can define actually a symplectic form omega underline with a property. So maybe let me write it here, that the pullback of omega underline gives you back the close to form omega twiddle. So this is an example of symplectic reduction. And moreover, I mean, under a bit more conditions, actually, you can find a one form alpha underline on the quotient, whose pullback is the form alpha twiddle, and you can find a vector field Q underline on the quotient, which has this property. Namely, if you take a function on the quotient, you can either first apply this new vector field and then pull it back to the original space of field, or first pull back and then apply the original Q. So you want this to happen for all the fields. So under some condition, this happens, this works. And now you can rewrite the error term we introduced here by saying that I mean, the condition that Q should be the Hamiltonian vector field of S is now spoiled by this term. So the pullback of this one form we have on this quotient space. And the interesting thing is that this one form is a potential for the symplectic structure you have here. So notice that on this quotient space, now we have a symplectic form of degree 0 and the function of degree 1. Well, actually, yeah, this Q probably, yeah, should write this condition. And here you also have the condition that this Q is the Hamiltonian vector field of this quotient. So this is a nice thing you can realize in the quotient. Not only that the symplectic form is invariant, but actually that the vector field you have in quotient is Hamiltonian with respect to some new function. So over here, you get this BFE structure. And actually, if you apply this directly to field theory, you can consider the cohomology of this Q underline, and this will give you a function on some symplectic reduction. This is so-called reduced phase space. But in addition, you have this relation between the structure you have on the space, original space of field F, and on this quotient, which is given here. Now, if we go back to our problem, the boundary problem, where S was this local action, Q was our original vector field, we knew that this condition was spoiled by boundary terms. So this means that this alpha, this alpha underlined here, or at the end of the construction, this alpha reduced, only depends on the vector fields on the boundary, actually, vector fields and their jets, including transversal jets. So this quotient space, F underlined, is so-called BV space of boundary fields. So correct notion of boundary fields arises precisely when you do this reduction. This reduction tells you what you have to consider. So, for example, if you consider usual classical mechanics where the field is a path Q, this construction eventually tells you that when you go to the boundary, which is just a point in this case, the coordinates of the phase space will be Q at, say, the initial point, and the velocity at the initial point, or better, the momentum at the initial point. So all these arises when you do this construction. But if you do it for more general field theory, including gauge theories and so on, this construction gives you the correct space of boundary fields. Of course, I have made some assumptions. This works in several nice cases, but sometimes it does not work. I mean, it's not. This is somehow a recipe that tells you what you have to do if you have a field theory on a manifold with boundary. And then the interesting thing is to check when the regularity conditions are satisfied or not. So when things work, then you have this BFE space of boundary fields and this equation that relates the bulk structure to the boundary structure. If you differentiate this equation, in particularly, you see that the Lie derivative with respect to Q of the original symplectic structure is a pullback of the symplectic structure on the boundary fields. Or, in other words, you can see that if you pull back the symplectic structure on the boundary field, you get something that is trivial in the Q cohomology. So in the Q cohomology, this pullback is 0, and says that something, something on which a symplectic structure vanishing is called in symplectic geometry an isotropic submanifold. And in nice cases, when this is maximal, this is called the Lagrangian. So this condition can be rephrased by saying that the projection from the bulk field to the boundary field is a Lagrangian structure. So this is a language in derived algebraic geometry, which has been developed for other problems, but actually appears also in field theory in this equation. But notice that this equation now is derived from this equation. So this is somehow a refined version of saying that you have this Lagrangian structure. And from the physical point of view, this equation is related to the fact that somehow solutions to the field equation in the bulk give you some Lagrangian, in good cases, give you some Lagrangian submanifold of the reduced phase space, and in particular tells you that you can now solve the Euler-Lagrange problem by imposing boundary conditions. So the boundary condition should be the choice of some other Lagrangian submanifold here. So these are the proper boundary condition. Then somehow the solution are obtained by intersecting the Lagrangian submanifold. You decide to choose the boundary condition with the canonical Lagrangian submanifold you get by this construction. There is another consequence of this equation that follows when you apply 1 second Q and you work out a bit. Essentially, and basically you also use this other equation here. So the equation that the Q on the reduced, on this BV space is a Hamiltonian vector field for this S, and use all the fact that this omega is underlined is exact. So putting everything together tells you that contracting omega with the Q twice gives you the pullback of this function on the boundary fields. But now, so the point that contracting omega Q twice is, roughly speaking, I mean, if there were no boundary, this would be exactly the Poisson bracket of S with itself. So setting this to 0 was the classical master equation. Now this tells you that this object, well, which is not well defined, but you reinterpret by this formula here, is not 0, but it's under control. It's a pullback of this boundary action. And well, this becomes important, especially when you want to do quantization. So now let me rephrase the gluing I presented before in a better way. So the idea is that when you have your manifold M and the space-time manifold M, and you cut it along a hypersurface, you get these two space-time manifolds, M1 and M2. You have the BV theory here and here. Then you use the above construction to construct the BFE theory over sigma. And so you associate with this BFE space, F underline. And now the correct space of fields on the glued manifold M is obtained as a fiber product over this space here. But now this is a fiber product, but you have these BV structures. In particular, all these objects here are complexes. The restriction maps are chain maps. And so this becomes a fiber product in the category of complexes. And so this is what is called a homotopy fiber product. And the nice thing is that now you can change these complexes by quasi-isomorphisms, as explained above. And what you end up with are different but equivalent construction for the space of fields here. Now, the interesting thing is that you might have examples of equivalent BV theory, namely this bulk BV equivalence I explained before. So let me go back a few slides. So this here, where you have like this pair of maps, phi and psi, between one space of fields and the other, compatible with the Q and Q prime, which form a quasi-isomorphism and preserve the actions and symplectic form in this relaxed way. Remember that I said, well, this produces equivalent theories. And I gave you as an example this equivalence between the Jacobi theory and 1D gravity with matter given by this Q. Now, if you have a boundary, it may happen that this equivalence is not compatible with the boundary. And precisely, this is a case when this happens. So this case is interesting because it's a simple one-dimensional case where you have this equivalence if you have no boundary. So we say then we are working on a circle, or when you ignore the boundary. But if you take the boundary into account, the equivalence fails. And this is actually interesting because this theory is a theory where the construction I presented, this reduction actually works. All the regularity conditions are satisfied, where this is a case where some of the regularity conditions fail. So in particular, you cannot really do this quotient in a nice way. So you can do something. You can associate some relaxed version of this structure. And it turns out that the equivalence you had in the bulk is an equivalence we have the relaxed structure, but fails precisely when you want to go down to the quotient, which is a nice thing. So this tells you that you might want to consider these bulk BV equivalencies because this is the tool you can use to get a nice boundary problem. Okay. And now let me finish in a few minutes just telling you, roughly speaking, what is the quantum version of all this. Somehow the idea is that if you have no symmetries in the functional integral approach, you define by considering the integral of the exponential of the action over the space of fields. Of course, we have to define this. There are different ways of this. One way is, for example, to do perturbation theory, consider Feynman diagrams, normalize them if you need on. But okay, I don't want to enter too technically. Suppose you have some way of defining this. What happens if you have symmetries? Well, you take this integral over some quotient, but this is somehow the bad way of doing things because the quotient might be singular or might lose all linearity properties and so on. The way in the BV language is some way essentially some nice way of rephrasing what the gauge fiction should be. So the idea is that now we have this space of fields, all symplectic manifold with function SPV that Poisson commutes with itself. Now the idea is that instead of going to a quotient, you take a submanifold. So name of this symplectic manifold, and what you do, you choose a bit arbitrarily a Lagrangian submanifold, but not completely arbitrarily. You choose a Lagrangian submanifold on which this integral makes sense. In the sense that, for example, if you want to do perturbation theory, you want to make sure that when you restrict this action to the Lagrangian submanifold, the critical points are isolated, so you can do formally the perturbation expansion around critical points. Now, the point is that, of course, now the answer depends on the choice of this Lagrangian submanifold to make sure that this choice is relevant. Here is where basically the BV construction, actually the original BV, also becomes important. So what BV observes, so I call it a theorem. So this is a theorem in finite dimensional version of this, and in some infinite dimensional version, what you have to say what you're doing. So the idea is the following, that first of all, there is delta, some other cohomology operator delta, different from the original Q, which squares to 0. And moreover, if this operator has the following property, if the BV action has the property that delta of this exponential is 0, then this integral is invariant under the formation of this L. So which means that it doesn't really matter, at least what L choose. You choose L to make the integral well-defined, then you can change this L and the result does not change. So these things are well-defined. Now, the interesting thing is that this delta is constructed in such a way that this equation, delta applied to exponential is 0, exactly when the Poisson bracket of this BV action with itself is 0 up to this term here. So not this term here is this operator delta applied to the BV action itself, but now at order h bar. So which means that perturbatively, at first you can ignore this term, and so you end up with the classical master equation, and then you have somehow to make sense of this extension here. So somehow, for example, if you work in perturbation theory, typically you do the two processes at the same time. You make sense of the perturbed expansion, and at the same time you make sense of this part of the quantum master equation. And now, an interesting thing is that you can do some partial integration. Namely, you assume that your space of field as an odd symplectic manifold is actually a product of two odd symplectic manifolds. And you assume that, well, your original action is a function on the whole space of fields, which satisfies the quantum master equation. But then you just choose a Lagrangian submanifold of the second factor and integrate over it. So the result will be a function on the first factor. I rewrite this, the result is again as an exponential. Well, typically you just take the logarithm of this to define this as 1. And now the theorem is that if this action S satisfies the quantum master equation, the resulting exponential you get here satisfies the quantum master equation with respect to the delta for the new space of fields F1. So this is a very simple exercise, but I think it was observed first, like maybe only 20 years ago. And it's quite useful because it has several applications. So, well, one application is the construction of observables. This was actually our original application. So you can construct very, very interesting observables for a field theory, starting from simple observables for another field theory, which is defined on the larger space. Another application, this was a loss of original idea, later on developed by Mignoff in this particular example, by Castello in general, is a BV compatible version of Wilson renormalization. So in this setting, you should think of F as a space of all fields, and then you split the fields into ultraviolet and infrared fields, and you integrate out the ultraviolet fields to get some effective action on the infrared field. But you want all of these to be compatible with the BV formalism because, right, you want to be sure that things do not depend on the choice of this Lagrangian and the choice of gauge fixing. And I mean, this result here tells you that this actually works. And one last application is a quantum equivalence of field theories, which, well, well, is better than the previous one I presented before, because this really tells you that the two theories are equivalent also at the quantum level. Namely, when you, for example, want to compute expectation values of observables. So in this setting, we say that two action, say, probably should say S1 is equivalent to S. If S1 is obtained from S by this procedure, and moreover, the associated map on observables is a quasi-isomorphism. So what is the associated maps on observables? So suppose that I have some function on the original space of fields. I can compute its partial expectation value. So I multiply my exponential of the action by this functional. I integrate on the Lagrangian submanifold on the second factor of the space of fields. I normalize by this integral. So this also, right? It's also Z of L1 of L. And okay, so if I do this construction, this will give me some function on the first factor. And so this construction gives you a map from the functions on the whole space of field to the function on the first factors in this decomposition. Okay, and now you can check which property this map has. And the nice case is where this map from these functions to this function is a quasi-isomorphism with respect to the differentials. And in this case, you can say that the two theories are equivalent. So they're really equivalent in the sense that you can now map observables on the theory, on the one theory to the other, and you can compute their expectation values in one or the other. So here are, several papers where this idea has been exploited, first in some examples and in general, then explicitly to consider equivalent theory, and some recent result, some recent application of this, and they are finished with this, is that, for example, with Francesco Bonecchi, Maxime Zabzin, we observed that actually you can obtain four-dimensional IAMP theory out of a four-dimensional topological theory using this kind of equivalence. So the idea that we want to explore this, well, what does this tell us about a physical IAMP theory, starting from something that's easier to deal with, namely a topological field theory. So I think I can stop here. And okay, thanks for your attention.
Well, thank you very much, Alberto, for this wonderful lecture. We have time for some questions. Are there any questions in the audience? Please feel free to unmute yourself or to write in the chat.
Oh, hi. May I ask a question?
Yep.
Yeah. Hi. Well, first, thank you for the beautiful lecture. I wish I would understand half of it, but it's very impressive. Could you comment more explicitly on the role that the dimension would play in this construction?
The dimensional space-time.
Yeah.
Or, well, it depends, of course. I mean, also the kind of field theory you consider. I mean, this is some general formalism. So you some F, some space of field, some action functional, and you do something. Then, of course, you have to specialize to some field theory, which means you specialize what is the dimensional space-time, what is the action, what are the symmetries, and so on. And then, of course, you get something specific. Now, of course, the role of dimension, I mean, just enters in this construction. So, for example, also normalizability, for example, and this follows the usual pattern. What is interesting is that there is this construction I presented before, this idea that you go from space-time to its boundary. And so in this case, you go, for example, from something, some dimension D, to something in dimension D minus 1. Of course, in dimension D, for example, you want to formulate quantization, and in dimension D minus 1, you have some classical problem in infinite dimensional symplectic geometry. But the interesting thing is that sometimes, in some cases, you can repeat this construction. So actually, you can go to corners of dimension 2 and so on. And so here, dimension plays a role in the sense that, well, you can start from dimension D, and then you have some associated construction dimension d-1, d-2, and so on. In nice case, up to dimension 0. And of course, depending on what the dimension d was at the beginning, right, you have different terms of associated structures you can consider. And of course, you have to understand what are these associated structures. And I mean, this is also work in progress. And yeah, I mean, I can tell you more if wishes, but
if I understand correctly, interesting things happen when you combine topology with analysis. You are assuming that the structures you are dealing with are smooth, and as we know,
yes.
under rescaling, smoothness degrades.
Yes.
So, do we have a definition of a theory in the ultraviolet limit, or do we have a series of constructs which keep some cutoff, which enables the topological language to proceed?
Well, this depends, of course, on the theory. So once you have a specific theory, you have to formulate this, and then I mean, sometimes you go back. I mean, the formulation is the usual one, but now you keep track also of the symmetries and the boundary in the appropriate way. But of course, when, for example, when you want to do this renormalization, where was it in this BV setting? Let me see. For example, Costello did it for general field theory, and let me see, what was it? Okay, let me see. Okay, here. I mean, I just briefly mentioned it here, but of course, here when you have to do things, you really have to formulate things correctly to say what it means to take ultraviolet fields, infrared fields, what is a propagators, how you construct the propagators, how you regularize the theory, and so on. You have to put these extra ingredients.
But
so this,
for example,
this is a general.
Yeah.
Yeah,
For
this is a very
example,
general.
no, sorry.
Yeah. No, you go. Yes.
For example, in early 70s, there was a construction of phi-4 field theory, where it was stated that here is a definition which was totally rigorous.
Yes.
It was constructed, although the authors left open the question of whether there is any phi-4 term left in the construction. Yes. So it's called phi-4 field theory because it was the limit of phi-4 field theories, but this particular limit does not have the term left in it.
Exactly. Yeah.
Do such considerations pop up in the purely topological description?
Well, topological depends also. I mean, okay. Typically, this is my area. We typically consider the perturbative expansion. So this, of course, doesn't have this problem. It's some formal description which would give you some asymptotic version of the theory if the theory exists. Otherwise, it gives you something, and of course, you have to interpret. For example, if you do phi-4 theory in 4 dimension, of course, you can formulate it in the perturbative approach. Then, of course, the result is that this perturbative approach does not correspond to a really constructive field theory. This is something else. Of course, then it's a different step you have to do. And okay, of course, yeah, I don't know how much one could do for this. I mean, these, of course, would be important things to do, but it's not been done. How to deal with constructive theory in this BV setting? Of course, the first example will be just like to formulate a constructive abelian Yang-Mills theory, for example. And this is done, I think, in lower dimension only, right? And of course, I mean, these are all interesting open problems.
Thank you.
Because one thing is, for example, there is also one version I didn't mention here, but of course is related to it by Kasia Reisner and Fredenhagen and so on, which is a way of obtaining again algebraic quantum field theory, also in the presence of symmetry in this setting. But again, they do it in the formal perturbative version as well. Of course, and this just gives you some formal algebra associated to causal region in space-time and so on. Then, of course, the question is like, okay, what is the constructive theory associated with this? And I think nobody knows that, apart, of course, from some very few examples. Of course, there is some intermediate thing you can do, something semi-classical, which is interesting. That, for example, what are the structures associated to boundaries and corners? Of course, so the boundary is something, I mean, not unexpected, is like the reduced phase space of the theory. But then there's somehow this construction tells you also what to associate to corners, for example, codimension 2. And here, basically, is a nice but conceptual way of seeing all the somehow asymptotic symmetries, for example, that your theory might have. And these are, of course, still classical, and then you can move to something maybe semi-classical, but this is something extra that you can get easily, well, not easy, but somehow more conceptually from this approach. Instead of just like guessing what the asymptotic symmetries should be, somehow you have a consistent framework to derive them.
Yeah, but to some extent, if there will be if in situations in which there is an ultraviolet limit, it's quite possible that the topological language then, in literal sense, starts to be very problematic. But the question is, what structures can one still retain?
Yes,
it's like Brownian motion, which can be smooth, which can be the ultraviolet limit of walks which are smooth on a certain scale, but the scaling limit is Brownian motion, and derivatives require some proper reinterpretations.
No, sure, yeah.
Thank you.
Okay, thank you. Are there any other questions? Okay, it doesn't seem to be the case, and time is running. So thank you all for coming for this talk. We're going to have another talk in 2 weeks with Hangser Yao, who is going to give the next seminar. I hope to see you all there. Thank you very much.
Thank you.
Okay, bye.